Hi, welcome to this second little video on efficiency analysis. And really this is not so much efficiency analysis as doing some sums. So the first thing we're going to do is just check an interesting sum that every computer scientist ought to know. And that's 1 plus 2 plus 3 plus ... up to n is equal to what? So if you had the proper math education, and which you have, and you remember, it's equal to n times n plus 1 over 2. So there's a closed form formula for that sum, but actually the big point here to remember in your future life is that you don't need exactness. So in terms that we were doing recently, all we want to know really is 1 plus 2 plus 3 ... up to n. What efficiency category is it in? So obviously it's in theta of n squared, because that's what this guy is. Because this is 1/2 n squared plus n over 2. So we've seen recently that that's big theta of n squared. But we want to see, like, what if you didn't actually know that and had to prove it? Well, there's a really good idea here, and that's to use an area. Represent this sum as an area. So we can do that by drawing. So we have 1, 2, 3, ... up to n, and then so each of these rectangles is 1 across its base, and this one is up to 1, and this one is up to 2, and this one is up to 3. So it's pretty easy, and this last ... and the last one is up to n. Okay, so the area of this one is obviously 1. The area of this one is the height of 2 times the base of 1. Height of 3 times the base of 1. So that's what they are. So the area of the rectangles is equal to the desired sum. So, of course, does that help? Sure, it helps, because we can do two things. The first one is, switching colors dramatically, we can prove that the sum, let's give this a name, let's call this S. So we can prove, S of n. So we can prove that S of n is in, the easy direction is to show it's in big O of n squared. And we can do that as follows. We just need to find, if we just go straight across, what's the area of this square? The area of this square is n squared. It's n across the base, and it's n high. So what we're saying here really is that 1 plus 2 plus 3 plus ... plus n is less than or equal to n plus n plus n plus n, which is, of course, n times n, or n squared. So that direction is really easy. But on the next page, what about showing that S of n, I'm going to switch back to black. What about showing that S of n is in big omega of n squared? To do that, we have to get a lower bound. And to get the lower bound, we've got this rectangle, and this rectangle, and this rectangle, all the way up to this last rectangle. So the right-hand edges of the rectangles are there. All right, so it's pretty clear that this function, so we're going to use the function f of x is equal to x. So here's the function f of x equals x. It hits 1 at 1, 2 at 2, 3 at 3, up to n at n. So that function is right there. So that function is f of n, f of x. However, it doesn't matter what you call the argument. All right, so if you look at this, it's pretty clear that the area under the curve is, in fact, what? It's the integral from 0 to n of f of x dx, which is actually the integral from 0 to n of x dx, and hopefully all of you can comfortably compute that as x squared over 2 evaluated between 0 and n, which is n squared over 2 minus 0 squared over 2, which is n squared over 2. So the point is that S of n is bigger than or equal to this area, because the sum, remember, is the rectangles. So these little triangles that are sticking up above the green function f of x equals x is the extra stuff. So in fact, S of n is bigger than or equal to n squared over 2, which is 2n squared. And that's exactly what we need, and that's true for all n bigger than or equal to 1. So those two quantities are what we need to prove that S of n is in big omega of n squared. So that was kind of an easy thing to do. And we're going to do a couple more examples of this same idea. Okay. So there's another common sum, which I mentioned last time in class, but the sum, if we want to add up 1 plus r squared plus dot 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 plus r to the n. And so if we say that's equal to s, so this is a very famous thing to do, so I'll go ahead and do it. If we say that that's equal to s, then we know that s times r is equal to, it's just multiplying all of these guys by r. So it's r plus, r squared plus r to the n plus r to the n plus 1. So what that tells us is that s minus s times r is equal to 1 plus r plus up to r to the n minus r plus r squared plus up to r to the n plus r to the n plus 1. And so of course the important thing here is the 1 doesn't cancel, but the r and the minus r cancels, and the r squared and the r squared all the way up to the r to the n and the r to the n. So the only thing we have left is this. So, and then here on this side we can factor out the s. So s can easily be seen to be 1 minus r to the n plus 1 over 1 minus r. And if we multiply the top and bottom by minus 1, we get the formula I stated without proof last time in class. Okay, so note something interesting. If r is bigger than 1, this quantity is approximately equal to r to the n, right? Because these terms are negligible, and the r to the n plus 1 over r gives you r. And if r is less than 1, this gives you, it's better to look at it this way. It gives you 1 minus r to the n plus 1 over 1 minus r. And so this number is just some fixed number, some constant. Or I should say the limit as n goes to infinity. So as n goes to infinity, this term disappears, and you just basically got, so it's very close for large n to 1 over 1 minus r. Okay, so, but I want to prove this a different way, because that was kind of a pain. So, the point here is that S of n in this case is in big theta of r to the n if r is bigger than 1, and it's in big theta of 1, so it's just a constant if r is less than 1. And of course, if r equals 1, some perverse person might have been saying that, if r equals 1, then this is 1, 1, 1, 1, 1, and it just adds up to theta of n. So you just have n ones added up. Okay, so let's add this up in a different way. Can we use areas? So here's what, let's look at the case that r is greater than 1. So the area of the rectangle, the first rectangle, so actually the first rectangle has height 1. So, and the second one has height r, and this third one has height r squared. And then way out here there's one that's called r. The nth one has height r to the n. So if we're adding up all these guys, and of course my scale doesn't work, but you know, exponential function grows incredibly fast. So the point is is kind of what's the area under this curve roughly, because this curve that goes through these points, this one, whoops, this one, so if we take the curve that goes through the right hand endpoints, more or less, that function we can use f of x is just equal to r to the x. So the sum is very close to the integral from whatever 0 to n of r to the x dx. Now this is a little harder to add up, so we'll just pretend that it's e to the, if r is equal to e, then we know what that is. It's the integral of 0 to n of e to the x dx. The antiderivative of e to the x is just e to the x. So we get something like e to the n minus e to the 0, which is e to the n minus 1, which is n theta of e to the n. So without, it's not too hard of a stretch. That's just a little side note. So it turns out that this guy has some different constant in front, right? Because you can convert r to the x is equal to e to the something else like log base r of x or something. Oh yeah, that's right, because these cancel to give r. So their point is it is an e to the x function with an extra number in there. So it turns out that the my sum is in theta of r to the n, just like we saw when we actually added it up carefully. Okay, I don't know if that helped, but now we're going to do a serious example. So let's look at another sum, which is the sum of squares. 1 squared plus 2 squared plus 3 squared plus dot 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 plus n squared. And of course what we really care is what theta is it in. Alright, so we'll use the same idea we used before. Let's just take rectangles. So let's take the rectangle at 1, and it will have height 1 squared. The rectangle's right edges at 2 will have height 2 squared, which is 4. So this sum is 1 plus 4 plus 9. So we take the rectangle out here, and that's the last one I'm going to draw. So the point is the general rectangle here, if its edge is k, the height is k squared. So what we're saying is the function we want to use here to compare this to is f of x equals x squared. Duh. So what can we say about the area of these guys? So the area from 0 to n of x squared dx is what? Well, it's x cubed over 3, evaluated between 0 and n, so it's 1/3 n cubed, which is in big theta of n cubed. Now, is this an exact proof? Actually, yes, because if we take the function x squared and go out to n, the area under the curve is exactly this, right? And the rectangles actually stick up above, so let me do the rectangles in a green color. So the rectangles all stick up above the curve. So what we've actually proven, if you're careful, is that we've proven that the sum, my sum of squares, is actually bigger. It's the green rectangle area. It's actually bigger than 1/3 n cubed. So that shows S of n is in big omega of n cubed. And what about the other direction? Well, the other direction is easy like it was before. So we can say S of n is 1 squared plus 2 squared plus da, 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 up to n squared, but that's less than or equal to, we just replace each one of these by something possibly bigger, n squared plus n squared plus n squared, which is n cubed. So that proves that S of n is in big O of n cubed. And if we want an area for that, we can just take this area. So this area is obviously n, and the right-hand side here is n squared. So this whole red area is n cubed, and obviously the area of the green rectangles is less than or equal to n cubed. I mean, you can do it algebraically or geometrically. So we've proven that S of n is bounded below by n cubed, a multiple of n cubed, and above by a multiple of n cubed, which is all we were trying to do. So I'm going to stop there. Hopefully that will help you as you work on the routine exercises for lesson, whatever it is, 3 or 4. Thanks.